This is the first part of Newton's unification process. What we're going to do here is we're going to use the law of universal gravitation, which by the way is sometimes referred to as Newtonian gravitation. We're going to use Newtonian gravitation to first of all show that all projectiles near the surface of the Earth fall with the same constant acceleration. In other words, we're going to be using Newtonian gravitation, this single physical principle, to explain that type of motion. I have it presented to us as a problem. Go ahead and copy the problem down in your notes as I read it to you here. Unification, part 1. Use Newtonian gravitation to demonstrate that all projectiles fall with the same constant acceleration near the Earth's surface, regardless of mass. That's, of course, Galileo's kinematics of a projectile. Right off the bat, however, Newton recognizes mathematically that there's a problem. For example, let's say that right here is the Earth, like so. And then here's an object of mass m near the surface of the Earth. Recall that, according to Newton's assumption about gravity, that every bit of matter in the universe exerts an attractive gravitational force on every other bit of matter in the universe. So imagine that I have two identical bits of matter associated with the Earth's volume. Let's say, for example, that there's a little bit of matter here, and that then exerts a gravitational force on the object of mass m, like so in this direction. Then let's say that further away from the mass m, I have an identical bit of matter associated with the Earth, say right here. And that bit of matter then also exerts an attractive gravitational force on the object, like so. Notice, by the way, that I drew this force vector here as being smaller in magnitude than this force vector, and the reason for that is because ultimately of the inverse square law, this bit of matter right here is further away from our object of mass m than this bit of matter is right here. So this gravitational force vector then therefore is smaller than this one for that reason. Regardless, however, what Newton realizes that he has to do is he has to mathematically add together all of these individual force vectors to get the net force of gravity exerted on the object due to the Earth. That requires three-dimensional calculus. Newton literally discovers the calculus that is necessary to make this calculation. So Newton realizes that he has to mathematically add together the force vectors over the entire volume of the Earth to obtain the net force of gravity exerted upon the object. That requires three-dimensional calculus. Newton literally discovers the calculus necessary to do this. It involves something called a triple integral. Newton discovers the calculus required to do so. Now that calculus, that three-dimensional calculus, is beyond the scope of this class. It's even beyond the scope of AP Physics C. Regardless, however, of the details of that calculation, the result that you get from that calculation is actually quite simple. The result of that calculation, that of course I'm skipping over here, is simply as follows. Mathematically, the Earth's gravity behaves as if the entire mass of the Earth was concentrated at a point at the Earth's geometrical center. This is the mathematical result of this three-dimensional calculus that is necessary that I'm skipping over here. So you ultimately end up with a pretty simple picture mathematically as to how the Earth's gravity behaves. So just very simply, the result of the calculation is that mathematically the net force of gravity exerted by the Earth behaves as if the entire mass of the Earth was concentrated at a point at the Earth's geometrical center. Make sure you pause if necessary to copy down all of this very important information. Of course, I'm just describing to you qualitatively the net result of this calculation that does require three-dimensional calculus. So you actually end up with a pretty simple picture, if you will, to describe the Earth's gravity. Here's then how I'll go ahead and describe that picture. So once again, make sure you had this copied down. And now let's go back to here. Okay, so now here's the entire volume of the Earth like so. And then right here now mathematically is how we treat the entire mass of the Earth as a point at the geometrical center. The mass of the Earth I'm going to label here as m sub e. Okay, and then right here is our object of mass m, for example, this marker, and it's in free fall here near the surface of the Earth. Okay, now according to Newton then, this then means that there's only one force exerted upon the marker, and that's the force of gravity like so. That is inwards towards the center of the Earth, where we now mathematically treat the entire mass of the Earth as being concentrated at. How do you then write F equals ma for this situation? Well, the left-hand side of the expression is the force of gravity that's exerted upon the marker when it's in free fall near the surface of the Earth. That's then equal to the following. Capital G, the universal gravitational constant, multiplied by the mass of the Earth, multiplied by the mass of the marker, and then divided by the distance between these 2 points squared. If you're just talking about motion near the surface of the Earth, then for all practical purposes, the distance between this point here and this point here is just equal to the radius of the Earth. Like so, which we'll now list here as capital R sub e. So that goes in the denominator here, squared like so, on the left-hand side of the expression. And then the right-hand side of the expression, of course, is just mass times acceleration. But we already know what the acceleration is because it was measured earlier by Galileo 50 years prior to Newton. It's 9.8 meters per second squared. It's small g, acceleration due to gravity. Like so. And now notice that the mass of the marker cancels. Like so. So then we're left with the following expression. Notice that the right-hand side of the expression, all of those numbers are constants. So because these numbers here are constants, this then means that acceleration due to gravity is a constant. 9.8 meters per second squared. All objects fall with the same constant acceleration, regardless of their mass. This is, in part, demonstrating Newton's intuition in understanding why the force of gravity has to be dependent upon the product of the masses. Because when we write this expression, the mass of the object cancels, giving us this result that we already know from Galileo 50 years prior. If you had written instead the force of gravity being dependent upon, say, the sum of the masses, would the small mass m then cancel from the expression? No. So then therefore this shows us Newton's intuition and understanding of the force of gravity has to be dependent upon the product of the masses and not necessarily, say, upon the sum of the masses. So ultimately we now have an explanation here for Galileo's result. So we have Galileo's kinematics of a projectile explained. Okay, now let's examine this expression here a little bit more carefully. Let's take a look at some of the numbers. For example, of course, small g. Small g is 9.8 meters per second squared. This, of course, was first measured by Galileo 50 years prior to Newton. have the radius of the Earth. We've known the radius of the Earth since the time of Eratosthenes, more than 2,000 years ago. The radius of the Earth is 6,400 kilometers, 6.4 times 10 to the 6 meters. This was first measured by Eratosthenes. Okay, and then we have capital G. Now, I've already quoted to you what capital G is equal to. In metric SI units, the universal gravitational constant is the following number. Okay, how it was first measured, which didn't occur until after Newton's death, by the way, I'll get to a little bit later on. But for now, if we know these three numbers, take a look at this expression here. What is the only unknown? The mass of the Earth, which we can now find. So let's go ahead and take this expression right here and cross-multiply and solve for the mass of the Earth. The mass of the Earth is small g times the radius of the Earth squared, and then divided by capital G. Of course, I found that by just cross-multiplying here and solving for the mass of the Earth. If you take these numbers in and plug them into here, we then end up with the mass of the Earth in terms of kilograms. The mass of the Earth in terms of kilograms is 6 times 10 to the 24. Like so. So that's how we know what the mass of the Earth is, because we had measured all of these numbers here. This then allows us to calculate the mass of the Earth from this expression. So what we've done here in the first part of this unification process is we've shown that a single physical principle, Newtonian gravitation, explains Galileo's kinematics of a projectile. It's explaining, in other words, for example, motion near the surface of the Earth. The second part of the unification process is to use Newtonian gravitation to then describe Kepler's laws of planetary motion. We'll do that in the next portion of this lecture.